it'll help me do this one question, which is actually pretty difficult. And when I do get questions about that, it helps me to be able to just point to a video that I've done and have people, hey, if you feel like you're completely lost, watch this video where I did this question from beginning to the end. Hopefully that helps you. Let me know of any follow-up questions, and we'll go from there. So let me start. It's a question in a portable TA actually, so you could also look at portable TA. But let me work through it. So block A and B sit on this ramp. They are attached by massless rope. That means a tension, well, massless rope over massless frictionless pulley means tension on both sides of the string will be the same. I'll be using that. Both segments are parallel to the surface. That's good. Block B is heavier. Block A. So let me note this, that there's no friction. Oops. I can't. Yeah, no friction there. I'll just remember that. And block B and the ramp, there's a friction. Okay, so part A, as usual, asks you to draw free body diagram. So I'll first draw and then give a word description for the submitted answer. And that's what you should do. You shouldn't just say, see attached work. And that gives you no credit whatsoever. So for A, which is easier, no friction, there's going to be gravity. There's always gravity. Am I given symbol for essay? No. I'll just assign a symbol. And then there will be tension force. Not tension force, sorry. There will be normal force. That's pointed this way. And then there will be tension force. Let's say normal force A, tension force. And let me do the free body diagram for B. It's a lot more complex for a couple reasons. So there's going to be gravity. That's the same. And going through the same reasoning as for A, there should be normal force from the table, that's or from the ramp that's supporting it. And then there's going to be a tension force, and I'm going to be using the same letter as for A to indicate that this is the same magnitude of force. And there's going to be friction, and I have to take a guess. Do I think mass B will be sliding downward or upward? Based on the fact that B is heavier, I think it will be sliding downward. In that case, the friction must be directed to opposite. So I need to have a friction force that's upward. And if you stop here, you will have missed one important force. You need to do what I call Newton's third law check. For every single force, you have to either decide it's an external force, so no Newton's third law pair needed, or it's an internal force and you need to label a Newton's third law pair. I mislabeled this. This should be NB. So I think with this is external force from Earth. External force from Earth. This is a little bit harder, but it's a force from the pulley. So this is external. So it's fine that there's no equal and opposite reaction force for either of these tension forces. The reaction force will be on the pulley. This force is from the ramp, external. Friction is from the ramp, external. And this is where you should realize that this is an internal force. You really need to draw the reaction force on B. And if you want, you can label this NA to indicate that it's equal in magnitude. So, but if you don't draw this reaction force pair, you will have missed some part of it. And that affects later part of your answer. So let me type this out. On A, how much time do I have? Yeah. Already used 5 minutes. On A, there are 3 forces: gravity, downward, tension along string, and normal force perpendicular to ramp. On B, there are, is it 5 forces? 1, 2, 3, 4, 5. Yeah, 5 forces: gravity, downward, tension along string, normal force from ramp, perpendicular away from ramp, normal force from A, opposite in direction to normal force on A, and friction guessing upward along ramp. And so one way you will check this guess later is if your friction force turns out to be negative, that means, oh, it must have been downward instead of upward. So assuming block B accelerates down the ramp after it's released, what is its acceleration? Oh yeah, your question had to tell you that. If it doesn't, it's possible that you will have static friction and have a zero acceleration. Now, because it told you that, you don't have static friction, you have kinetic friction. So, so you need to go through the rest of the standard strategy. So I've done, so let me just spell out the standard strategy steps. Or B, your standard strategy steps are 1, free body diagram. I'm just abbreviating it. 2, you have to draw axis. 3, you have to break forces into components. 4, you need to write down net force is equal to mass times acceleration. So I need to define my axis. So I think my mass A will accelerate upward. Because mass B is accelerating downward. So these will be my positive x directions. That makes my equation writing simpler, helps avoid the potential sign errors. So with that direction of axis and y-axis being this way, my forces that I need to break down are just my gravity. So gravity will be broken down into this and this components. This and this components, and you need to have a sense of your angles. So this is my auxiliary figure for angle. This is the angle theta you are given. So you have to locate this theta in your triangle here. It's not gonna be here because that's 90 degrees minus theta, and it's gonna be here. This will be the theta. You should have practice going through the geometric exercise. So with this, I can quickly write down these component values, and I'll do that as I'm doing step 4, writing down my Newton's second law equations. I'm gonna have one equation each for each direction for each object. So I got 2 objects, 2 directions each. I got 4 equations to deal with. So let me just write them down. I have net force on A in the x direction is gonna be tension minus MAG. This is the opposite side, so it should be sine theta is equal to mass times acceleration. Yeah, upward, that's gonna be the direction it will be accelerating. Net force on A in the y direction will be normal force minus this component of gravity, which is adjacent to the angle. So it will be MAG cosine theta is equal to 0. I need a net force on B along x. This time gravity is positive because this is my direction of acceleration that I'll be setting as positive. So opposite side, MBG sine theta minus, you got 2 forces opposing it. Tension minus the friction force is equal to MA, MB times acceleration. Same acceleration magnitude because, kind of connected together, string isn't stretching. Finally, net force on B along the y direction. Normal force, B, minus, you got 2 forces, this and this component of gravity. So minus NA minus MBG cosine theta is equal to 0. So what is its acceleration? Okay, 10 minutes. I think I have enough time. It says show your work in the attached work. Now, as you look at it, counting unknowns, you'll find out that you have 5 unknowns. Tension is unknown, acceleration is unknown, normal force is unknown, friction is unknown, this normal force NB is another unknown 5. So what you need is a fifth equation saying the friction force is equal to mu times NA. That's your fifth equation, introducing no new unknowns. So yeah, now I got 5 equations. Looks like I only need acceleration for part B. So let me just eliminate everything that's not acceleration. And it looks like in part C I need a tension, so I'll eliminate tension second to last. So let me go through this algebra as quickly as I can. I'm just gonna plug this. Let me solve for NA first. So I know NA is equal to MAG cosine theta. And I'm gonna, using that here, I'm gonna solve for NB. NB is equal to, oh, I don't need that actually. And doing the algebra in my head, it's MA plus MB times G cosine theta, which kind of makes sense. Using these two, I can have an expression for friction force, which is mu MAG cosine theta. And it's at this step, I think I should write down simplified versions of equations 1 and 2. So my simplified versions of equations 1, T minus MAG sine theta is equal to MAA. Equation 2, MBG sine theta minus T minus the friction, mu mg cosine theta is equal to MBA. And how much time do I have? 8 minutes. Yeah, let me do it this way. So I'm gonna solve the simplest equation for tension first, and then plug it in here to eliminate tension. So I get T is equal to MAA plus MAG sine theta. Plugging it in there, I get MBG sine theta minus of both of these, minus MAA minus MAG sine theta minus mu mg, oops, that should have been MBG cosine theta is equal to MBA. So I collected like terms, one that depends on A on the right hand side, and then solve for A. And I'm gonna do that in my head, doing that in the interest time. Doing that in my head, I get A is equal to everything on the left hand side that was on the left hand side, just added it together. That's gonna be MA plus MB times G sine theta. That's these two terms. Minus. Yeah. So actually, let me do it this way. MB, that, minus MA, and then minus mu MBG cosine theta divided by sum of these two, MA plus MB. So I had to say here, acceleration is equal to, and there are no numbers to plug in, so I just type in this whole expression. And so minus MA. And as long as MB is greater than MA, yeah, your acceleration will be positive. G times sine theta minus mu times MB times G times cosine theta. And if you somehow get a negative answer here with the numbers plugged in, that actually means what the question told you. This is wrong assumption. It must be static, static friction instead, and your acceleration is 0 and all that. MA plus MB. So yeah, I think that's good. For work, see attached. What is tension in the rope? So, I do have time to actually write it out, but let me just do something that will be acceptable to me if you do this and you're out of time. So you can say T is equal to MA times A plus MA times G times sine theta, using A in part B E above. So, I do have time to, plug this in and get an expression. But if you are out of time and you just express things this way, that's acceptable. Because here this A is a known quantity. And you can just, reference that known quantity here. That's fine. For work, C attached. And, I would prefer if you took the time to plug this in, simplify. And in this particular question, it won't really simplify all that much because of the friction. In a frictionless case, it does simplify somewhat, but so we are over time, so let's not, over time in the sense of virtual class session, so let's not belabor that. So this would be, I guess, parts B and C. They're kind of the same thing. Or there's no, they're not really separated. So right, let me attach work, since I have time to attach work. This is how you should be attaching work. Or is that actually, so this isn't how you should be attaching work. So when you're attaching work, I recommend that you take some time to organize your work. And so here I'm just doing it this way to save a little bit of time, but so you can attach work after you've submitted. You don't have to do it within the time limit. So what I would ask you to do is, take some time to organize your work. Here, I've organized this somewhat as I was going along, but it would be better if I took some time to, solve the C. I don't have time to solve for C, and maybe put in a few words of explanation of what am I doing here. Those help. So that's what I would recommend. I'm not doing what I'm recommending because what I recommend takes time and it feels like I don't have a lot of time. So I'm just, do what I preach, not what I practice. So I'm just gonna submit that. Now, after submitting, if you want to change your, and you can save work here also, but if you want to change your work after you've gone this far, maybe you did all this and an hour later you figure out, oh, I missed that, and you want to correct it in your attached work, which you can. If you go to this, come to this item, or let me refresh, then you will see this button that says add work. When you go through that add work button, the work is still editable. You can change it. So so that's if you figure out you made a mistake, hey, correct it this way. The system does timestamp your work, so I can see when it was attached, and if it took a reasonable amount of time between when your work answer was submitted and when your work was last attached, it's fine. If it took you more than a day, then I might ask you, hey, why did it take you more than a day? But reasonable amount of time, a few hours, it's all totally fine.